This is going to be 8.7, part 2. So when we left off, we were talking about characteristics that make a fractal, and we were on the third one, which is recursion. So I gave you an example of a Sierpinski triangle, and now this is an example of what's called the Koch snowflake. So it's a really pretty fractal, and I want to show it to you. So here is 4 iterations, or actually 3 iterations of the Koch snowflake. And the recursive rule for each iteration is to take each side and remove its middle third. And then what we're going to take, and we're going to replace that middle third with an equilateral triangle without its base. An equilateral triangle means that all sides are of equal length and all angles are of equal length as well. So basically what happens is you have a triangle where all the interior angles are 60 degrees and all the lengths are of exactly the same side. By the way, the Koch snowflake starts out with an equilateral triangle. So, for instance, if we have a triangle and we remove the middle third, like I'm just doing this on the one side of it, and then I replace it with an equilateral triangle missing its base, I get a shape that looks like this. So if I do the same process to the base, and I do the same process, take out the middle third of all the sides, that's how I get to the next iteration. Excuse me. So I keep on doing this to every single side, and that's how I go from one iteration to the next. I'm going to go ahead and erase that. And that is known as the Koch snowflake. So the next page shows you an example of a snowflake. Snowflakes kind of look like the Koch snowflake. It's a little bit different, but it generally has the shape of it. And a snowflake is definitely a fractal. That's just how water crystallizes. So it's really neat. Okay, so the fourth criteria for something to be a fractal is it has to have fractal dimension. You will need a calculator that has scientific functions on it. Okay, because you're going to have to use logarithms, which is abbreviated as log, to be able to figure out the fractal dimension. Okay, so fractals have dimensions that's in between either the first and second dimension or the second and third dimensions. And this should be the word R. All right, what is a fractal dimension? Fractal dimension is a ratio that shows the statistical index of complexity, how detail in the pattern changes with scale. So remember, we always have scale with fractals. So we're looking at how complex is this fractal dimension. Ratio means we're going to take 2 objects and we're going to divide them. That's what makes up a ratio, one object divided by another. So the formula is D equals log of n over log of r. N is the number of self-similar objects. D stands for fractal dimension. And the little r is the number of smaller objects after the recursive rule is applied on one side of the figure. Okay, so let me read that out. Normally, R, and it should be a little r, Little r is the number of smaller objects after the recursive rule is applied on one side of the figure. So the Sierpinski triangle here below shows 2 iterations. We start with no iteration, which is an equilateral triangle. Remember, the recursive rule is to find the midpoints of each and every triangle, and then we pop out that piece. So that's what we're doing here and how we're getting from one iteration to the next. So we're going to find the fractal dimension of the first iteration and the second iteration and see if they are the same. So let me go back. I didn't realize I broke this up that way, but that's okay. All right, so we're going to find the fractal dimension. So let me grab a pen that is not yellow. So D equals, we're going to take the log of the number of pieces. So I'm looking at this first iteration here. So the number of triangles that I have that are solid are 3. Over the log of R, remember, is the number of smaller objects after the recursive rule is applied on one side of the figure. So I'm looking at this side. I only have to look at one side. So I'm looking at this side right here. How many pieces do I have? 1, 2. So there are 2 pieces on each side. And you can check the other sides as well. They're going to have the same thing. If I look at this side, how many pieces do I have? 2. If I look at this side, how many pieces do I have? 2. Okay, so I just wanted to show you how I am determining how many pieces I have on the side. So I have log of n, which is the number of pieces, over log of r, where r is the number of pieces on one side, which in this case is 2. So now I have to divide d equals log of 3 over log of 2. Okay? I'm also going to look at the second iteration, and I'm going to actually do the math in a moment. So for the second iteration, d equals log of the number of pieces. So in the second iteration, there are 9 solid triangles over log of the number of pieces on one side. So once again, I'm just looking at one side because all the sides are the same. And I'm going to count how many pieces do I have. I have 1, 2, 3, 4. So log of 9 over log of 4. Okay, we're going to figure out this math on the next page. So the fractal dimension of the first iteration is d equals log of 3 over log of 2. And the second iteration was d equals log of 9 over log of 4. Okay, when you enter this in your calculator, you're going to look for a key that says log, that stands for logarithms, and you're going to use it. So log of 3 over log of 2, I get d equals 1.58, and I am simplifying this or rounding to the hundredths place. And when I take log of 9 divided by log of 4, I get d equals 1.58. So if you notice, it doesn't matter how many times we go up in iterations, we're going to get 1.58. That is the fractal dimension. That is the fractal dimension. So we can conclude that the fractal dimension is complex, and it is in between the first and second dimensions. The reason why I knew that is because our value is 1.58. So that's in between the first and second dimensions. Really interesting, right, guys? Okay, so that was fractal dimension, which is the fourth criteria for something to be a fractal. Now we're going to look at the last two, which is the fifth one. The object must exhibit the shape and has to be unpredictable in its order. So basically it's saying that if there's one small change in the recursive process, chaos ensues. So you're always going to see the study of fractals with chaos. Okay, fractals with chaos theory. This is also known when we say that if one small change creates chaos, It's also called the butterfly effect. And the butterfly effect, defined with respects to chaos theory, is a phenomenon whereas a minute localized change in a complex system can have a large effect somewhere else. So the reason why it's called butterfly is because there's a theory that states that if a butterfly beats its wings in Chicago, it can create a tornado in Tokyo. If you want more information, look it up on YouTube. There's tons of videos talking about the butterfly effect and chaos theory. So once again, fractals and chaos go hand in hand. And for an object to be a fractal, one of the criteria, it has to have unpredictability in its order. So number 6, or the last criteria for something to be a fractal, is the object is bounded infinitively. That means that by the use of the recursive process, remember we use the rule, we can infinitely apply the rule to the object. So if you measure the length of the side of a fractal, the higher the iteration, the higher the iteration, we're going to find that the length becomes infinite. So it's really crazy. So let's check that out. So here's an example of the Koch snowflake. And here's 0 iterations, 1, 2, 3, 4, and 5 iterations. And once again, we can keep on going indefinitely. So if you remember, the iteration or the recursive rule of the Koch snowflake is to remove the middle third and replace it with an equilateral triangle missing its base. So we do that on all sides that are available to us. So if we look at an object being bounded infinitely, we are looking at, one side. So if I measure this side, I'll get some length, right? So if I go to the first iteration, now one of my sides is this. So if you look at that, I'm going to have to measure length from here to here, from here to here, from here to here, from here to here. And if you do that, you'll notice that it is longer than the 0 iteration. So now let's go into the second iteration. And here was the original line. So I'm measuring from here to here, from here to here, and I'm going all the way around. So all the way around this shape. And I noticed as I'm going around, that whole length is getting longer and longer. So that whole side there is the length of it. And I'm not even going to touch the third one, guys, because it's going to be really tricky. But you can see the length of the side gets longer and longer as we go up iterations. And in fact, the length of the Koch snowflake increases by a factor of 43. That is really, really big. That's more than, doubling or tripling. That's like times 43 every single time we do this. So the larger the iteration, the length gets closer and closer to infinity. So that's a symbol for infinity. So those are the 6 criteria that make a fractal a fractal. Make sure you know all 6 of them and what they mean on the test, because it's definitely on there. It may not be on your homework, by the way, but it is definitely on the test, okay? All right. Happy studying.